Welcome to Math with Professor V. In this video, I'll be solving or working through the final exam that I gave my Calculus 3 class last fall. And just as a warning, the exam covers primarily the topics from the last unit on vector calculus. I put a couple questions from earlier in the semester, honestly just to give them some easier problems to work with. But the majority is everything in chapter 16 if you're using Stewart's calculus. Okay, so let's jump right into it. It was 10 questions, 10 points a problem. They have over 2 hours. So calculate the requested distance. We want the distance from the point 3, negative 8, 8 to the line x equals 2 plus 3t, y equals 3 plus 12t, and z equals 7 plus 4t. There's a variety of ways you can solve this problem. I'm going to do it maybe a little differently than I've done it before, just to, spice things up for everybody. So we have some line whose parametric equations were given to us up above. I'm going to call this line L. And here's line L's parametric equations. And we want the distance from the line to some point over here called S, with coordinates 3, negative 8, 8. Now, when we want a distance, obviously we mean the shortest distance. Otherwise, there's infinitely many different distances you could give. But nope, this is the one that we want right here. Here's the distance. And so what we're going to do is I need to pick some point on the line, P, and connect it to the point S. So how can I come up with a point that's on the line? Well, I have the parametric equations of the line. Can you extract a point from there? I think the easiest thing to do is just let t, your parameter, equal 0. And then you would get x is 2, y is 3, z is 7. So that's my point P, 2, 3, 7. Okay, it's now connected to the point S. If you look here, yes, I have made a right triangle. So I can find the distance d by the Pythagorean theorem. However, I need to find a few things first before I go ahead and compute the distance d. First, I would need to figure out what is the length of the hypotenuse of this triangle. Well, the hypotenuse of that triangle is magnitude of PS. Can we get that? Yeah. Okay, so let's go ahead and do that first. So the vector PS, I'm just going to take the coordinates of S and subtract the coordinates of P. Hopefully you're pro at doing that right now. So PS would be 1, negative 11, 1. Now I want the magnitude of PS. So that's going to be square root 1 plus negative 11 squared is 121 plus 1. So this is rad 123. Okay, so I have this side under control. Now, what's the length of this side in the triangle? So let's think back when we were studying projections. What we learned was that we could take a vector and then find its scalar projection along another vector. And that's exactly what I'm going to do. I want to find the scalar projection of PS along or in the direction of this line here. That way I can figure out what the length of this little side here is in my triangle. So we have to be a bit careful. We have to be careful. First thing, I want to project PS in the direction of L. So I need a vector in the direction of L. Well, fortunately for us, they gave us the parametric equations for the line. So the direction vector of the line I can find by just looking at the coefficients of t right here. So I'm going to say my direction vector V has components 3, 12, 4. Okay, now what we're going to do is take the scalar projection of PS along the vector V. But one moment, we need the scalar projection of PS along V. Now, this scalar projection involves a dot product between these two vectors. And this scalar projection will come out to be a negative quantity if the angle between these two vectors is greater than 90. And I don't know, I've taken a three-dimensional situation and I've drawn it in somewhat of a two-dimensional fashion. So I'm not entirely sure that the angle between these two vectors is less than 90. So, the way I have it drawn here, yes, it is. But what can I do to guarantee that I get the scalar projection between these two vectors where there's an acute angle between them? I just take the absolute value afterwards. Okay, that way I don't get a negative scalar projection. So I'm basically forcing it so that I have the same situation matching my drawing. I have an acute angle between these two vectors. Okay, so this distance right here is going to be, let me shrink this down and move it over here. That's the length of that side right there. Okay, so let's go ahead and compute it. So scalar projection of PS along V, and we're going to take the absolute value just in case. That's going to be absolute value of PS dotted with V divided by magnitude of V. PS dotted with V. Can we do it in our head? 1 times 3 minus 11 times 12. So minus 132 plus 4 over, I'm going to need absolute value, magnitude of V, which is rad 9 plus 144 plus 6. So yes, the numerator was going to be negative 125, but now I'm going to make it positive 125. Denominator is rad 169, so 13. Okay, perfect. So now I know the length of this side in the triangle, that's magnitude of PS. I have the length of this side, that's absolute value of scalar projection PS along V. I'm going to do good old Pythagorean theorem now to find the distance D. How lovely. So let's write out our Pythagorean theorem, D squared plus what we just found, scalar projection of PS along V, 125 over 13 squared equals magnitude of PS squared, which is going to be just 123. Okay, then from here, solving D squared is going to be, I already started getting a common denominator, so we would have 123 minus 125 squared is 15625 over 169. So this is 20,787 minus 15,625 over 169. And then distance ends up being square root 5,162 over 13. Okay, good job. There's a couple other ways to do this problem. So if you've seen me do something differently before, that's why. Okay, let's move on now. Change the Cartesian integral to an equivalent polar integral and then evaluate. You must include a labeled graph of the integration region, which would be just a two-dimensional region. So we have double integral 0 to natural log of 2, 0 to rad natural log of 2 squared minus y squared. The integrand is e to the rad x squared plus y squared dx dy. And they're already telling us that we need to switch this into polar coordinates. Okay, so first thing I want you to do, we're going to graph the integration region before we do any sort of switcheroo. Let's look here. The limits for y go from 0 to natural log of 2. I'm looking at the outermost limits of integration. So let's write that down. Y goes from 0 to natural log of 2. And then x goes from 0 to radical ln of 2 squared minus y squared. Now you should recognize that this is the equation of semicircle. It's the right half of a semicircle. Oh me, oh my. If you forgot that, remember x squared plus y squared equals r squared. That's a circle. If I get x by itself, then you would have r squared minus y squared. So x is plus or minus radical r squared minus y squared. If we have only the positive radical, then it's just the right half of the circle. The minus sign would give us the left half of the circle. And I can see here that the radius of the circle is none other than good old natural log of 2. So let's go ahead and sketch out the integration region, because that's going to help us figure out what the limits should be when we switch to polar coordinates, okay? I mean, if you're very good at imagining the graph in your head, you could do it that way, but I give my students points for including the graph on the exam, so you might as well. You might as well. Even if you don't get points for it, I would graph it. So I know the circle's radius is natural log of 2. I know I drew the whole thing in, but I'm only going to shade the integration region. So watch. Y goes from 0 to ln of 2. So y is restricted from 0 to ln of 2. But then x is restricted from 0 to the right half of the circle. So then x is restricting just this portion here. Because x equals 0, remember, is the y-axis. So the integration region is just this quarter here in quadrant 1 of the circle with radius and natural log of 2. Okay, good. So if we're going to go polar then, we need to figure out what the limits of integration should be in terms of theta and r. Well, hopefully theta is pretty straightforward. We're only in the first quadrant, so theta is going to go from 0 to pi halves. 0 to pi halves. And then to figure out r, just start at the origin, start at the center, and then just draw a little line segment going out. You can keep going or you can just stop. Where it starts is the lower limit of integration. Where it hits next is the upper limit of integration. So we're going to go from, that's right, 0 to natural log of 2. Okay. Other thing, we have to change the integrand to also be in terms of polar coordinates. So instead of e to the rad x squared plus y squared, that's going to be e to the rad r squared, or e to the r. So let's hop to it. We're going to have 0 to pi halves, 0 to ln of 2, e to the r, and then just be careful. dx dy gets replaced with, very good, r dr d theta. Beautiful. Now, I'm looking here, all my limits are constants, right? And I don't even have any thetas in this integral, so I can break things up. I can write this as integral 0 to pi halves d theta, and then 0 to natural log of 2. I'm going to write it as r e to the r dr. Okay, and then if you've done a bunch of these, at this point, you know this is just going to give you pi halves. In fact, I'm totally fine if my students notice, here's a d theta, here's 0 to pi over 2, and then in the very next line they write pi halves. Not a problem for me. In fact, I love it. So now all we have to do is tackle this little integral, which looks pretty harmless. I mean, you did this back when you were in Calc 2, just fresh little student. Didn't even know that there was so much math ahead of you. So it's time to do it by parts. We're going to let u equal r, and then dv would be e to the r dr. So du is dr, and then v is e to the r. Yeah. Okay, so I have this pi halves hanging outside from this first little integral. And then now I have u times v, so that would be r e to the r. That's going to get evaluated from 0 to ln of 2 minus integral v du. So e to the r dr, and that's from 0 to ln of 2. Okay, beautiful. Almost done. So this is pi halves times r e to the r minus, let me take this antiderivative and then I'll evaluate everybody together from 0 to ln of 2. So just e to the r, 0 to ln of 2. Let me plug in the upper limit. So this is pi halves times ln of 2 e to the ln of 2 minus e to the ln of 2. That's the upper limit. Minus lower limit would be 0 minus e to the 0, which is 1. And then this is just a 2. This is just a 2. So I have 2 natural log of 2 minus 2 plus 1. Yes? Yes, Professor V. Okay, so we have pi over 2 times 2 natural log of 2 minus 2 plus 1 is minus 1. And there's our final answer. Okay, beautiful. That one hopefully wasn't too bad. I think pretty much everyone got it right. Pretty much everyone got everything right on the final. They did so well last semester. I was amazed. Okay, very good. I gave another page, but we don't need it. Next, evaluate the line integral along the curve C. So we have x squared plus y squared over z squared ds, and then C is the curve given by the following. R of t equals 10 sine 1/2 t, 10 cosine 1/2 t, 12t, and t is between 2 and 4. Okay, so if you'll remember, when we're evaluating line integrals, ds is equal to magnitude of r prime of t dt. So I'm going to need to compute r prime of t, take its magnitude. That way we can compute this line integral. And then the limits of integration are going to be the limits that they gave me for t right here, from 2 to 4. So first, let me just rewrite r of t so we can see the components clearly. 10 sine 1/2 t, 10 cosine 1/2 t, and then 12t. Okay, so r prime of t. Don't forget the chain rule because of these 1/2s that are in front of the t. That 1/2 is part of the argument, okay? If you need to add extra parentheses, do it. So derivative of 10 sine 1/2 t would be 10 cosine 1/2 t times a half. So then it would become 5 cosine 1/2 t, yes? Good. Similarly, the next component would be negative 5 sine 1/2 t, and then the last component's derivative is just 12. So now I'm going to take magnitude of r prime of t. So that would be square root of the sum of the squares of the components. So this would be 25 cosine squared 1/2 t plus 25 sine squared 1/2 t plus 144. Very good. Now I can factor out the 25 from the first two terms under the radical, and you have cosine squared 1/2 t plus sine squared 1/2 t, and then plus 144, just hanging out, minding its own business, being a champion, because we know cosine squared theta plus sine squared theta is just 1. In this case, my theta is 1/2 t. So I just have 25 times 1 plus 144, which is 169. So this is rad 169, which is 13. Yay! Okay, so then that tells me ds is going to be 13 dt in this problem. Pretty nice. Only other thing we need to do is substitute in x, y, and z to all be in terms of t, the way the curve is defined. So let's do that first so we don't have too much writing. X squared plus y squared over z squared would be 10 sine 1/2 t squared plus 10 cosine 1/2 t squared over z squared. That would be 144 t squared. And then if you look here, the numerator, it's going to be 100 sine squared t, or 100 sine squared 1/2 t plus 100 cosine squared 1/2 t. That's just going to give me 100 over 144 t squared. So that's my integrand. Then let's hop to it. So we have integral along C, x squared plus y squared over z squared ds. Now I'm going to rewrite the limits of integration to be in terms of t. So it's going to go from 2 to 4. X squared plus y squared over z squared is 100 over 144 t squared. And then ds we know is 13 dt. Very good. What should you do first? Oh my goodness, you're going to take all these constants out of the integral so they stop harassing you immediately. So you're going to have 1300 divided by 144. Yes, I want you to do that first. And then you have integral from 2 to 4. 1 over t squared, that's t to the negative second. Rewrite it that way so we can take the antiderivative more easily. Okay. And then 1300 over 144, that's 650 over 72. Okay. Taking the antiderivative of t to the negative second, we're going to add 1 to the exponent, divide by the new exponent. So it's going to be t to the negative first, dividing everything by -1, same as multiplying. And then this is going to get evaluated from 2 to 4. Leave the constant out of the party. It's not invited, okay? Good. So then let's see. We have negative 650 over 72 times t to the negative first, that's 1 over t. So this would be 1/4 minus 1/2. So this gives me a negative 1/4, right? Very good. So then 72 times 4, that would be 288. And then this would become positive 650 over 288, which reduces to 325 over 144. I do give them a calculator in Calc 3. Can you believe it? I take it away during Calc 1 and 2, and then sometimes for Calc 3, it's just harder to get the numbers to turn out right. So sometimes I'm like, have your little calculator back. Okay, third one done and dusted. Moving on to question 4. So find the work done by F over the curve in the direction of increasing t. And I gave them a little hint. You do not actually need to compute the line integral. So what we're going to do instead is prove that the vector field here is conservative. And therefore, that would make it independent of path. And so to find the work, all I would need to do is find the potential function, lowercase f, of the vector field, and evaluate f at the end point of the curve, subtracting f at the beginning of the curve. I'll walk you through the process. Don't you worry. So first, let's look at this vector field f. Let me rewrite the components without I hat, j hat, k hat, so you can really focus on what's going on. So it's x e to the 4x squared, e to the 2y, and then e to the 8z. Okay, so what I want to do is show f is conservative. And if it's a conservative vector field, we know that means that f is independent of path. Okay, so there's 3 conditions that we need to check in order to prove that a vector field is conservative. First, we have to show that the mixed partials are equal to each other. So I'm going to check del p del y is equal to del q del x. Well, let's see. So remember, this is p, q, r. Del p del y would just be 0. Does that equal del q del x? So here's q. Yeah, del q del x is also 0. Okay. If you forgot, I'll remind you. It goes p, q, r. Oh, I didn't write del q del x. That was the point. That one's good. Then I have to check del q del z. Does that equal del r del y? So del q del z, yep, that's 0. And del r del y, that's 0 again. Okay. And then the last one that I need to check is del p del z equals del r del x. Does it? Del p, that's 0. Del r del x is also 0. Okay. So there's 3 combinations. It should make sense. Like p, the partial of p with respect to y should equal partial of q with respect to x, and vice versa. And then you just mix and match all of the components. Okay. Second thing I need to check is that p, q, and r have continuous first partials, that they are C1 functions. And yeah, if I'm looking at p, q, and r, if I took first partials of all of these, I would just end up with exponential polynomial functions. Those are continuous on all real numbers, so we're good to go. And then the third thing I need to check is that the domain of my vector field is open and simply connected. So look at the domain of the vector field. The domain would be all of R3, right? We have no restrictions, and this is a three-dimensional vector field. And R3 is definitely open and simply connected. If you've forgotten any of these topics and stuff, don't worry. I have linked in the description all of the video lectures that correspond to the chapter on vector calculus. And then if you need to like go way back in time and review, then just go to the full Calc 3 video lectures playlist. Okay, so all three conditions are satisfied. So this means F is conservative and therefore independent of path. Okay, so then what I'm going to need to do is find the potential function. The potential function f of x, y, z. So how do we do that? Well, we look at the vector field. The first component is the partial of this potential function with respect to x. So x e to the 4x squared. The second component is the partial derivative of the potential function with respect to y, which would be e to the 2y. And then last component is partial with respect to z of the potential function, e to the 8z. So now let's just take antiderivatives, partial antiderivatives basically, and try to find the potential function. So I'm taking antiderivative with respect to x. You can write a full-blown integral, but hopefully at this point, like you're pretty under control in Calc 3 to do this in your head. So if you did a u sub, you would let u equal 4x squared, right? And then du would be 8x dx, but there's no 8. So then this would just be 1/8 e to the 4x squared. And then I have to say there could have been some function, I'll call it g, of y and z. So if this was my potential function, right, and I take the partial derivative with respect to x, then I would take the derivative of 1/8 e to the 4x squared. I'd get x e to the 4x squared. But I also could have other terms that only involve y and z. And if I take the partial with respect to x, then obviously the derivative of those terms would be 0. So I have to say, there might be more stuff only involving y's and z's. Okay, the next two are easier. So taking antiderivative with respect to y, f would be 1/2 e to the 2y, yes. And then I possibly have some h of x and z. Additional terms, a function involving only x's and z's. And then similarly, last antiderivative, so f would be 1/8 e to the 8z plus h, I don't want to use I, j, k, I don't like l, let's go m of x and y. So then now we just kind of put everything all together. So my potential function f of x, y, z would be 1/8 e to the 4x squared plus 1/2 e to the 2y plus 1/8 e to the 8z. Now you could put plus c plus some constant, and it would just end up canceling out when you compute the work. Okay, so you can put it, you can not put it, it doesn't really affect our outcome. And you'll see why in just a second. So what I'm going to do now in order to compute the work, since my vector field is independent of path, all I need to do is take the potential function, evaluate it at the end of the path, minus evaluating the potential function at the beginning of the path. So let's check back and see where did the path start and where did it stop. So we went from starting point 0, 0, 0, so that's the start or that's the beginning, to 1, 1, 0. Nobody cares because that's not our final point. Then we kept going from 1, 1, 0 to 1, 1, 1. So that's the ending point right there. Okay, so we're going to go potential function lowercase f of 1, 1, 1 minus potential function lowercase f of 0, 0, 0. Okay, here we go. So we need f of 1, 1, 1 minus f of 0, 0, 0. So you could see here, if there was like a plus c, you would have plus c minus plus c. So that's why we don't write it. If you don't believe me though, sometimes it's like hard when your teacher tells you, oh, you can skip this step. You're like, but why? Then just do it until you trust it yourself, you know. 1/8 e to the 4th plus 1/2 e squared plus 1/8 e to the 8th. Yes. F of 1, 1, 1. Minus f of 0, 0 would just be 1/8 plus 1/2 plus 1/8. Okay. Do these clean up? No, it's all different powers of e, so we're just going to leave them. 1/8 e to the 4th plus 1/2 e squared plus 1/8 e to the 8th. What is this going to be? 2/8, so that's 1/4, plus 1/2, that's 3/4. So minus 3/4. Here's our final answer. That's the work. Believe me, this was better than having to do a line integral. So yay! Thank you so much. All right, moving on. I give extra pages, you never know. Using Green's theorem, calculate the area of the indicated region. You must include a clearly labeled graph of the region. So we're looking for the area bounded above by y equals 2x squared and below by y equals 4x cubed. So first, let's go ahead and graph the region. I'm going to need to find the intersection of these two curves in order to do so. And then we're going to talk about how to use Green's theorem to find the area of the region. So first, let's find their intersection. It's a parabola and a cubic function, right? So you can probably already imagine what their intersection is going to look like. Don't divide by a variable, right? You know better by now. 4x cubed minus, you set it equal to 0. That's right. Take out the GCF, which is 2x squared, and you're going to have 2x minus 1 left. So then I get x is 0, or x is 1/2, okay? So since they're intersecting at values of x that are smaller than 1, the cubic function is going to be below the quadratic function, yes? Okay, so they're going to intersect at the origin at 0, 0, and at 1/2. And you know what? I'm just going to, we don't really need the y value. So they're going to intersect right there. So I'm going to say this is 4x cubed. And then 2x squared is just going to be above it. Okay, so I want the area of this little region here that looks like a banana. It looks like a banana. Okay, so how do we do it using Green's theorem? You have a couple different versions of formula for area. I'll just use this one here, area along closed curve, line integral, okay? C is a closed path, and we'll do x dy. Now, the region has to be traversed by C counterclockwise, okay? And it needs to be a closed path because we're finding the area of some bounded region bounded by C. So we need a counterclockwise path, so we're going to have to go up 4x cubed. So we'll start at 0, 0, and then we have to go up to this point here. And then once we arrive here at this intersection, the other intersection, then we're going to come back down to x squared. So I'm going to need two separate curves, right, in order to create a closed path C. So I'll call this first one here, this is C1. That's going to take me from the origin up to this point here. And then C2 is going to take me from the other point of intersection back to the origin. We need to parameterize these curves. So C1, that one's the easy one. I'm just going to go ahead, let x equal t. Y would be then 4t cubed because we're traveling along 4x cubed. And then the limits for t just match the limits for x since x is equal to t. So t is going to go from 0 to 1/2. And then I'm already thinking ahead. So my integral is x dy. That's the version of the area I'm going to use. You have a couple other choices. So I need the differential dy. So I'm going to come here, take the derivative. And I know dy equals 12t squared dt. Good? Okay, now curve 2 is a little trickier because I need it to start right here where x is equal to 1/2. And your parameter can never be decreasing, okay? So you can't just say, oh, I'm gonna make t go from 1/2 to 0. No, that doesn't work, guys, okay? So what do you do instead? I just think of it this way. Wherever you want to start, you take that number, that constant, minus your parameter t. So C2, I'm going to define x to be 1/2 minus t. And then as long as t goes from 0 to 1/2, you'll see it's going to go in the correct direction, because if t starts at 0, x will be 1/2, so we'll be right here. And then as t increases all the way up until 1/2, at the very end when t is 1/2, x will be 0. So that forces us to go backwards. So wherever you want to start, whatever that constant is, you let x, or usually it's x, yeah, be that number minus t, okay? And then from there, y would be, well, you look at the curve that you're on. You're on 2x squared. That's what y equals. So y would be 2x, which is 1/2 minus t squared. Good? That's the harder curve to parameterize, right? Because you have to force the direction of motion to go from 1/2 to 0. But we're good. Look at us surviving and thriving. And then since I'm just using this same area formula, let me find dy right now. So derivative would be 4, right? And then we have to use the chain rule. So it's 4 times 1/2 minus t to the first times -1, derivative of the inside, dt. So let me rewrite this. dy is -4 1/2 minus t dt. How we doing? Good. The worst is over. Parameterizing the curves is the hardest part of this problem. Drawing the region, coming up with this step. Now you just get to relax while you do an integral. And it's going to be like a cute integral like you used to do back in Calc 1. Okay. So area is going to be line integral along our closed path C x dy. And then nicely, you see we have the same limits for t, so we can just put everything all together in one integral. I can write it separately though if you want. So you can go 0 to 1/2. C1 is x dy, so x is t, and then dy is 12t squared dt. This is for C1. Plus, and then again for C2, 0 to 1/2, x dy would be 1/2 minus t, and then dy is -4 1/2 minus t dt. So this is for C2. But you see, they both have the same limits of integration. I can just combine them into one integral. So we're just going to go 0 to 1/2. This is going to be 12t cubed. And then be careful here. This is going to be -4 times 1/2 minus t squared. -4 1/2 minus t squared. And then all of this dt. Okay. We should be good to take the antiderivative right now. So antiderivative of 12t cubed would be, yes, 3t to the 4th. You guys, I'm not going to use sub for this. You should be able to do it in your head. You're just going to divide by an extra negative, right? So add 1 to the exponent, divide by the new exponent, and divide by an extra negative. This would be plus 4/3 1/2 minus t cubed. And we're evaluating all of this from 0 to 1/2. Are you all right? Yeah, you're great. You guys got this. Okay, so let's plug in the limits of integration now. So we've got 3 times 1/2 to the 4th, that's 1/16, plus 4/3 times 1/2 minus 1/2, oh, okay, that's 0. That's the upper limit. Minus lower limit is 0. Plus 4/3 times 1/2 minus 0 cubed, so that's 1/8. That's my tummy. Oh my goodness, I'm hungry. Okay, I got up at 5 to record this video. So this is 3/16 plus 0 minus 0. 4 over 24 becomes 1/6. Yes? Yes. Common denominator here is 48. So times 3 times 8. So what's that going to give me? 9 minus 8 over 48, if I'm not mistaken. So 1 over 48. That's the area. Now, obviously, it would have been easier if we didn't use Green's theorem and you just did your beginning calc way of doing top curve minus bottom curve. You could confirm that you did it correctly that way, but we had to follow instructions and use Green's theorem, okay? So this is definitely a tricky problem, something a lot of students need a little extra practice on, finding area with Green's theorem. Okay, let's do one though a little easier. Green's theorem again, but this time we're going to use Green's theorem to compute work. Okay, so using Green's theorem, compute the counterclockwise circulation of F around the closed curve C. This is just another way of saying find the work. Okay, find the work. You must include a clearly labeled graph of the region enclosed by C. So here's my vector field F, and it's just two-dimensional vector field, okay? So x squared plus y squared, and then x minus y. And C is the rectangle with vertices at 0, 0, 1, 0, 1, 6, and 0, 6. Okay, so let's draw C, and then the region that it's enclosing. This is 1. Here's y. I'll say this is 6. You know, it's your graph. Just draw it how you want it. 0, 0, 1, 0, 1, 6, 0, 6. Okay. Here, here. Oops. Scoot over. I probably should have drawn the lines first and then put the dots, but whatever. Okay, so we know we have 2. If we're going to use Green's theorem, follow the path around the region counterclockwise. Okay, here's the region D. Did they call it D? Some books call it D, some books call it R. Okay, whatever. D. And then here's my vector field, components P and Q. So we know using Green's theorem, if we want to find the work, if you're given line integral along some closed curve, f dr. Instead, you can compute double integral over the region D of del q del x minus del p del y dA. So instead of computing the line integral, you can compute double integral over the region bounded by the curve in order to compute the work. So that's what we're going to do, because notice here they gave me vector field and they gave me a curve C, closed curve, and instead of computing the work this way, I'm going to go ahead and compute a double integral. Okay, well, look at the region. I don't think we need to switch to any other coordinate system. I think we can just stay rectangular. Let me look at what del q del x minus del p del y looks like. Maybe I don't want to integrate it in rectangular, but this doesn't look like too crazy of a vector field, so I think we can just stay put. Del q del x is 1, and del p del y is 2y. So I think we're going to be good. We're going to just stay rectangular, okay? So the work is going to be double integral over D, 1 minus 2y dA. I'm just going to write dA right now to keep it vague. But yeah, we're going to stay in the xy plane. We're totally fine. It's a rectangle. How relaxing. Limits for x go from 0 to 1. Limits from y go from 0 to 6. So let's set it up. I'll just do x last. 0 to 1, 0 to 6, 1 minus 2y dy dx. And there's no x's in this entire integral. Do you see that? Limits are all constant. So I can just already get rid of 0 to 1 dx and multiply by 1 minus 0, upper minus lower limit. So that's just 1. And then you have 0 to 6, 1 minus 2y dy. Oh, and this integral is no big deal. We're going to have y minus y squared from 0 to 6. So what's that going to be? 6 minus 36 minus 0, so negative 30. Boom, boom. So that one's done. How was that? I think that was easier than question 5. All right, moving on. We're past the halfway point of the exam. I gave extra pages because, you know, things can happen. Find the surface area of the surface S, you must include a clearly labeled graph of the integration region, 2D. So remember, if you're finding surface area, it's just going to be double integral over your surface ds. Okay. Now, in this case, S is the portion of the paraboloid z equals 100 minus x squared minus y squared that lies above the ring x squared plus y squared greater than or equal to 25, less than or equal to 49 in the xy plane. Okay, so I'm going to just draw the roughest of sketches for you. You didn't have to do the 3D sketch. Notice I just asked for the 2D sketch, but let me just motivate it. So here's 100. And I know it's going to intersect here, 10, the xy plane, right? Okay. And they want the portion, the surface area that lies above the ring, where we have basically circles of radius 5 and 7 in the xy plane. So you can imagine, like, here's 5, here's 7. And you come up here, you just want that little portion of the surface area. So like that little patch of the paraboloid that lies above this ring. So we only want the surface area for this little strip that goes all the way around. Okay, you didn't need the 3D graph, but I just want you to understand what the heck is going on here. Okay. Now, since my surface is defined as a function of x and y, that tells me how we're going to define ds. So ds is always based on the surface. So I'm going to use for ds square root partial of z with respect to x squared plus partial of z with respect to y squared plus 1 dA. So let's compute that right now, and then we can decide to like what coordinate system we want to integrate over. So partial with respect to x would be negative 2x squared plus partial with respect to y, negative 2y squared plus 1 dA. So this is going to be radical 4x squared plus 4y squared plus 1 dA. Okay. Our integration region is this ring in the xy plane. Let's draw it. I have it very sloppily here in the 3D version, so you can probably already imagine what's going on. It's going to look like a very skinny donut. Ooh, a donut sounds good, you know. I have not had breakfast. Okay, I'm not going to draw this to scale. I'm just going to stretch it a wee bit. Ooh, I like it. I like it. Okay, so this is radius 7, and then this is radius 5, because it's bounded between 25 and 49. So this is the ring. We're finding surface area of the paraboloid above this ring. Excuse my sloppy coloring. Okay. Boom. All right. So I'm looking at things, if we're going to evaluate this integral, and we have this ds situation going on, x squareds and y squareds and circles make me think, ooh, we should go polar, right? We don't want to stay in the Cartesian coordinate system. Absolutely not. So if we go polar, what would be the limits now of integration over this region? Well, theta would have to go 0 to 2 pi, right? This region determines your limits of integration, what you want the surface area over. And then ds you compute using the surface. Do you see? This paraboloid has nothing to do with the limits of integration or the integration region. We're finding its surface area over this portion, this ring. Okay, then r should go between 5 and 7, right? From here to here, from here to here, all the way around. And then if we're going to go polar, okay, this is 4 times x squared plus y squared plus 1. Yes? So then that would be radical 4r squared plus 1. And I know dA is r dr d theta. So we are ready for business, people. Here we go. So surface area is going to be integral 0 to 2 pi, 5 to 7, rad 4r squared plus 1, r dr d theta. Yay. Okay. Now let's see. There's no thetas in my integral, so I can get rid of theta and 0 to 2 pi just by multiplying by 2 pi minus 0, which is 2 pi, yes. So I'm going to have 2 pi sitting outside. Then we have integral 5 to 7. Let me write that r in the front, and then rad 4r squared plus 1 dr. Now, if you need to do a u sub, you can, okay? You would let u be 4r squared plus 1. Let me write this off to the side. You could let u equal 4r squared plus 1, and then du would be 8r dr, which I pretty much have. I just only have r dr. So then 1/8 du is r dr. So all you're going to do is pick up a 1/8 when you take the antiderivative, and that r is going to go away. I'm going to save myself the hassle and just, boom, go for it. And I encourage my Calc 3 students to do this too, if they feel ready. So we're going to have 2 pi times 1/8, and then I'm going to now have 4r squared plus 1 raised to the 3/2 power when I take the antiderivative, because currently it's raised to the 1/2 power because of the square root. Then when we integrate, we multiply by the reciprocal of the new exponent, so 2/3. And then this is all going to get evaluated from 5 to 7. But you know, keep the constants out. Like you can just evaluate the variable quantity only. Just evaluate this part from 5 to 7 and then clean this all up and take care of it at the end, right? Okay, so let's see. This is going to be, that cancels with the 8, and now I just have a 2 down there. So we've got pi over 6 times, okay, 4 times 7 squared, so 4 times 49 plus 1, that's going to be 197 to the 3/2, minus 4 times 25 plus 1, that's 101 to the 3/2. Honestly, I don't care if they left it like that. I'm fine. I think a lot of the times in the back of the book with similar homework exercises, they rewrite it as like 197 rad 197 minus 101 rad 101. I don't think it cleans it up any better, so I'll take either, and you'll get full credit if you're in my class. Okay, I'll box this one, but this one's totally great as well. Whatever, live your life. Okay, so we just found surface area. That means you do double integral ds. That's it. No function here. A surface integral is a totally different thing, okay? Good, good, good. At the end, we're at the end. Question 8. Find the flux of the curl of field F through the shell S. You must include a clearly labeled graph of the surface, so a 3D graph, and the integration region, a 2D graph. So what does this mean? Flux of the curl of field F through the shell S. That's just work again. So remember, work can be defined also as surface integral, right? Over S. We have curl of F dotted with N ds. You basically, in this whole unit on vector calculus, are finding two quantities. You're either finding work or you're finding flux. So you just have to get straight which quantity you're finding and which version of the formula you're using, okay? So here's our vector field. Let me write it out. Vector field F has components negative 3z, 3x, and 9y. S is the portion of the cone z equals 5 rad x squared plus y squared below the plane z equals 4. Okay, so I'm going to find the curl of F. N is always going to be normal to the surface. So you use whatever surface they gave you to figure out what N is going to be, okay? And then we're going to clean up. We'll find the curl of F, dot it with N, and then we'll set up our integral all together, okay? First, let's find the curl of f. That part's a little easier maybe than finding your normal vector. So curl of f, I'm just going to set up my little determinant, I hat, j hat, k hat. Then we have del x, del y, del z, and then negative 3z, 3x, 9y. Okay. So here we go. This is gone, this is gone. Partial with respect to y of 9y would be 9 minus partial of 3x with respect to z, that's 0. So this is just 9. Then for the next component, I just imagine multiplying in the opposite order so I don't have to add an extra negative. So this would be negative 3 minus 0, so just negative 3. And then last component, if that's gone, that's gone. Partial with respect to x is 3, and then that's minus 0. So 3. Okay, how nice. Curl of f, just a bunch of constants. Now, to get the normal vector, we're going to graph this cone. It's opening up along the z-axis. The 5 just stretches it vertically. Okay, so don't have a panic attack. We're just going to draw a normal looking cone. Opening up along the z-axis. It's just the upper half of the cone. X, Y, just, you know, we're just casually sketching something. It's not intersecting with anything else. Oh, yes, it is. It's below the plane z equals 4. Then you know what? That's exactly what this is. This is z equals 4. Boom, that cuts my cone. Okay, now, the normal vector is always normal to the surface. Standard orientation is outward. So here's the thing that's a little bit tricky. Let me shade in my surface. Your normal vector, this surface is a function of x and y. So my normal vector would either have components partial with respect to x, partial with respect to y, negative 1, or it would be the other way around, negative partial with respect to x, negative partial with respect to y, positive 1. How do you know which one it is? Just look at your surface, okay? What direction is outward? And the easiest way to tell is at the extremes of the surface, like where it has a max or where it has a min. So everything, orientation should be outward from the normal vector. And if you look right here, yes, at the tip of the cone, imagine someone standing on the cone, you, and you have to be pointing outward. Your head cannot go into the surface, which means here's you hanging out on the surface, okay? Give me a vector that tells me which direction your head is pointing. Your head would be pointing in 0, 0, negative 1, wouldn't it? Okay, so since the z component is negative 1, then this is the version of the normal vector that we're going to use for the surface. Okay, so that's what I tell my students to do. Draw a little person, you, whoever, on the surface at the extreme point, okay? And then whichever way your head's pointing, that'll tell you whether z is going to be negative 1 or positive 1. If you had one of those paraboloids opening downward, say we had a different kind of surface, and you're at the top, right? Your head's pointing upward, then you would use this version for the normal. So just draw a little stick figure, and the head will tell you which the direction z needs to be in. Okay, so we're not using this one. Good? Now, whose partials do you take? This is all based on the surface. This is all based on the surface. The surface is the cone. So the vector field you use for the curl, right? The normal vector and these partials are all based on the surface. Don't get it jumbled up. Also look at the notation. Like this z, this is not a vector valued function. So this is, you could say f of x, y, right? So then it makes sense these partials come from the surface. This is a vector field, curl of f. So, you know, we can't take partials for this normal vector here of it. Okay, are we keeping things straight? I know there's just a lot to jumble up. Okay, so here we go. We're going to take partial derivative of the cone, my surface, with respect to x. And I taught my students this shortcut. It's life-changing. So when you have derivative of a square root quantity and you have to do the chain rule, you take 2 and the original radical expression, put it in the denominator. So you'd have 2 rad x squared plus y squared And then you multiply by the derivative of the inside in the numerator, that's the chain rule part, and derivative of x squared is 2x. And then that 5's just hanging out, okay, comes along for the ride. So there's the derivative with respect to x, and you could see these 2's will cancel out. And then similarly, if I take the derivative with respect to y, I'm just going to be left with 5y over radical x squared plus y squared. And then I know z is just -1. Okay. So now let's go ahead. Let's take the curl of f. Why am I writing so ugly? Excuse me. Curl of f. And let's dot it with n. Okay. So we're going to take 9 times this first component, and then -3 times this, etc. You know how to do a dot product, for crying out loud. Okay, so this would be 9 times 5x, 45x, over rad x squared plus y squared. And then I'd have minus 15y over rad x squared plus y squared minus 3. Yes? Okay, so go back. If I'm going to compute the work, then I need double integral of this quantity over my surface S. So, I don't want to stay in the rectangular coordinate system. Do you? No. Okay. Now, if we imagine the projection of this surface in the xy plane, then we're going to get a nice integration region if we switch to polar coordinates. So let's go ahead and draw that. I did also say in the directions that they needed to include a graph of the integration region. So we did the 3D graph already, the surface. Now we're going to go ahead and graph the integration region in the xy plane. Okay, so to draw the integration region in the xy plane, what I want to do is see, okay, I have my surface here, I have this cone, and it intersects the plane z equals 4. So I'm going to set those two equal to each other, and then draw that intersection, which is going to be in the xy plane, in a separate graph, okay? So I'm going to set 5 rad x squared plus y squared equal to 4. I'm setting the cone equal to the plane. So then I have rad x squared plus y squared is 4/5, which means we have x squared plus y squared equals 4/5 squared. And I'm just going to leave it like that. So the integration region in the xy plane is just a circle centered at the origin, radius 4/5, yes? Here we go. The radius is 4/5, and this is the entire region that we're integrating over. Okay, look back at the original 3D graph. That should make sense. That's where this is. Boom, 4/5. 4/5, and then you could see like there's the circle. Okay, so it makes sense, especially since we have like all these rad x squared plus y squareds going on. Let's go polar, right? So we're gonna go polar. Limits for theta should be 0 to 2 pi. Look at this 2D graph. And then limits for r are gonna be 0 to 4/5. Okay. Beautiful. So here we go. Let me write everything out. So we have original formula up top. Work was double integral over S, curl of f dot n ds. And then I have curl of f dot n right here. If we were to write it in polar, we're going to switch all of the x's to r cosine theta. And then these rad x squareds plus y squareds are just going to become r's. Okay? Here we go. Let's just hop to it. So limits, double integral limits are going to be polar limits. 0 to 2 pi, 0 to 4/5. Curl of f dot n, I'm switching to polar right now. So it's 45 r cosine theta over r minus 15 r sine theta over r minus 3. Yes? Whew. And then ds is going to be rd theta. And we're good. Okay. I can't do my cute little multiply by 2 pi trick because notice, oof, we have thetas this time in the integrand. But we can cancel and do some stuff first, so it won't be so bad. These r's cancel, right? Okay, and then if I look here, this is exclusively a function of theta. And then this is just a function of r by itself. So I could break this up into a product of two single variable integrals. So I can rewrite this as integral 0 to 2 pi of 45 cosine theta minus 15 sine theta minus 3 d theta. I should have written 2 pi. Where'd 25 come from? I'm losing my mind. Okay. And then next one would be for r, 0 to 4/5 r dr. So that makes it a little easier. And then I think we're ready to integrate each of them, right? Yeah. So this is going to be antiderivative 45 sine theta plus 15 cosine theta minus 3 theta. We'll evaluate that from 0 to 2 pi. And then over here I have 1/2 r squared from 0 to 4/5. Okay, so let's plug in 2 pi. 45 times sine of 2 pi, that's 0, plus 15 cosine of 2 pi is 1, minus 6 pi, minus, let me plug in 0. So that's 0, that'll be minus 15 plus 0. And then we have 1/2 times 4/5 squared, so 16 over 25 minus 0. Why was this one a random parentheses? That's going to drive me bonkers. Okay, so let's see what's going on. This 15 cancels with this 15, and everybody else was a bunch of zeros. What a bunch of losers. So all I've got is negative 6 pi times, this will cancel. So then I have 8 over 25. Nothing's going to reduce, right? So this is negative 48 pi over 25. That was a beast of a problem. I know. That one's hard. We practiced it in class, though. They weren't like blindsided, believe you me. All right. We're almost at the end. I think divergence theorem's one of the easier ones in the whole unit. So we're getting there. Okay. Enough of work. Let's do some flux. So find the flux of the vector field F across the surface S in the indicated direction. You must include a clearly labeled graph of the surface 3D and the integration region 2D. So here's my vector field F, components 6x, 6y, 7. And then if we're computing flux, the formula looks so similar to the one for work. It just doesn't have curl of F. It's just F dot n ds. So double integral over your surface S, F dot n ds, okay? No curl of F. Curl of F makes it work. No curl, it's flux. I made a chart for my students to summarize the two quantities, work and flux, and all the different formulas. I should probably do that for you guys in a little summary video. Okay. And what is the surface here? It's the nose of the paraboloid z equals 3x squared plus 3y squared cut by the plane z equals 3, direction is outward. Okay, so we know this paraboloid's opening upwards along the z-axis. If it's cut by the plane z equals 3, right, dividing by 3, x squared plus y squared equals 1, that intersection projected in the xy plane is just going to look like the unit circle. Let's draw this. This is going to be great. So, paraboloid opening upward, x, y, okay, and it's cut up here by the plane z equals 3. Let me just make like a cute bowl. Yes, we love it. And then you can imagine it's cut by the plane, and right here, this is 1. This is 1. So the region that we're going to integrate over is just, I'm assuming we're probably going to go polar again, you know. and just integrate in the xy plane. Let me shade in though the surface. Boom, boom, boom. Okay, so no curl of f. We're just going to do f dotted with n ds. N is always based on the surface. It has to be normal to the surface. They told me orientation is outward. That's our standard orientation. Okay, so normal vector, which version do we use? Because we have two versions. It could be partial with respect to x, partial with respect to y, -1, or it could be negative partial with respect to x, negative partial with respect to y, +1. Which one applies? Did you draw you a little stick figure at the very bottom, at the origin? You can just imagine it. You could say, hey, here I am hanging out on the surface. Your head is pointing in -z direction, right? If you were to write a vector representing this little stick figure, it would be 0, 0, -1. So this is the version of the normal that we're going to use to get normal to the surface. Okay, so partial with respect to the surface, partial with respect to x of 3x squared plus 3y squared. That would be 6x. Partial with respect to y, 6y, and then z is just -1. Okay, then we're going to take f dotted with n. F is right up above. So it's 36x squared plus 36y squared minus 7. And let's go ahead, let's draw our integration region, but I already told you we're going to go polar, right? You can probably see it makes the most sense because in the xy plane, we have this circle here. Boom. Does that look somewhat centered? Good enough. So here's 1, 1. We're integrating over this circle. So limits for theta should just go 0 to 2 pi, and limits for r 0 to 1. So this circle here is this little circle down there. Okay, good. All right, perfect. So let's go ahead, calculate the flux. We're going to have integral 0 to 2 pi, 0 to 1. F dot n, if I switch to polar, would be 36r squared minus 7. And then now I have r d theta since we're in polar. Beautiful. Ooh, this one's easier than the last one. There's no thetas in sight, right? In the integrand. Perfect. Then I can just get rid of the d theta and this outer integral and just slap a 2 pi on here. Bam, you get a 2 pi. Then we have 0 to 1. Just distribute this r through. So this is 36r cubed minus 7r dr. Good? Okay. Then leave that 2 pi out, minding its own business. This is going to be 9r to the 4th minus 7 halves r squared from 0 to 1. And then what is this? 2 pi times 9 minus 7 halves. 9 minus 7 halves. That's 18 halves minus 7 halves. So 11 halves. 2 pi times 11 halves. That's just 11 pi. Okay. Is that it? Did we do everything they wanted? Let's make sure. Keep that healthy paranoia. You must include a clearly labeled graph of the surface. We did it. And integration region. We did it. Okay. Fabulous. Last one. I guess I didn't need all these extra pages. Using the divergence theorem, find the outward flux of F across the boundary of the region D. You must include a clearly labeled graph of the region, 3D graph, yes? Okay, so here's F. I know it looks scary, but it has like a really cute divergence, okay? So F is gonna be, let me write it so you can see the components better. X rad x squared plus y squared, y rad x squared plus y squared, and then z rad x squared plus y squared. And then D is the thick cylinder, x squared plus y squared bounded between and including 1 and 4. And then Z goes from 2 to 6. Okay, so we'll graph that in just a second. Let me just remind you, when we're using divergence theorem, flux is triple integral over your solid E. And then you have divergence of F dV. So we're going to find the divergence of the vector field. And then dV is based on whatever solid we're integrating over. And the limits of integration are based, again, on this solid. It's a thick cylinder. So it's a cylinder that has, you know, a thickness to it. Let's graph it. Let's get that part done with. X is between 1 and 2. Okay. So X is between 1 and 2. And so is Y. So let's get this guy going. And then here. And then Z is between 2 and 6. So I'll say this is 2 and this is 6. Okay. And basically these are going to get projected upward. Something like that. And then this one as well. Boom. Maybe not so high. Okay. But the solid is only the portion from 2 to 6. So let me just shade this in without getting carried away. It's just going to be from here to here. So all of this, it's going to come around the back. And it's hollow in the middle, okay? It's hollow in the middle. It's this, all of the, let me do a different color for that part, hold on. I'm not happy. Not happy with my artistry. Okay. Yes, can you kind of imagine what's going on? And it obviously like the back as well. That's all part of the solid. Okay, so hollow in the middle, only Z from 2 to 6, and then that like kind of thick band because we're between 1 and 2. All right. Oh, they're calling it D, not E. I'm so sorry. Then let me call it, usually though, D is for two-dimensional regions. I'm gonna change this. Let's call it E. It's making me angry. Okay. So I just need the divergence of F. And then we'll set this triple integral up. It's looking like a cylinder already, so I feel like we should just do cylindrical coordinates. Don't you agree? Let's come up with the limits already. So we'll use cylindrical. So theta would go 0 to 2 pi. R would be between 1 and 2. And then Z, 2 to 6. See how easy? Okay. Let's get the divergence of F. Divergence of F, if you forgot, is del P del X plus del Q del Y plus del R del Z. So del P del X, let's see. Let me do that first. I have to do product rule, don't I? Del P del X, yeah. So derivative of X is 1, and then you would leave rad X squared plus Y squared alone. Plus, now I leave X alone, and I'm taking derivative of rad X squared plus Y squared with respect to X. So I'd have 2X over 2X rad X squared plus Y squared. And notice the 2X just cancels out completely. Okay. And then if I take the partial with respect to Y of the next component, it's going to basically be identical. The only difference is I'd have a Y here, and then the 2 Y's cancel out. So I'm just going to put plus rad, it would be X squared plus Y squared again, plus Y squared over rad X squared plus Y squared, plus, and then in this case, when I do partial with respect to Z, I don't need to do the product rule because there's no Z's here in the radical expression. So partial with respect to z would just be rad x squared plus y squared. Okay, so let's see what's going on. I have 1, 2, 3 rad x squared plus y squareds. And then I have an x squared plus a y squared over rad x squared plus y squared. So let me just get a common denominator for everything. Or if I know I'm going cylindrical, let's just substitute in right now. Everywhere you see x squared plus y squared, put an r, because we know we're going to cylindrical anyways, right? So 3 rad x squared plus y squared, that's just going to be 3r plus, and then x squared plus y squared, that's r squared over another r. So I have 3r plus r. So this is 4r. Woohoo! That's basically our integrand, almost, right? That's divergence of f. Then we just have dv, which since we decided to do cylindrical coordinates is going to be r dz dr d theta. Okay, we're ready to roll. Last problem. Oh, it's the end of an era. Oh, it's such an ugly looking flux, excuse me. There we go, that one's cuter. For some reason, when I look at the symbol for flux, I know it's just a Greek letter, but it reminds me of like those little alien toys in Toy Story that were in the claw machine. The ones that I don't know, they were so cute. They look like that to me. Okay, 0 to 2 pi. R goes from 1 to 2. Z goes from 2 to 6. Divergence of f is 4r, and then we're in cylindrical, so we need another r, dz dr d theta. You guys, great news. I don't see a theta in sight. So I'm just going to multiply by 2 pi. And then also, you know, that 4, what is he doing there? Get him out. So 2 pi times 4. And then I have integral 1 to 2. And then we have 2 to 6. And it's r squared dz dr. Well, you can break it up. There's no z's, guys. There's no z's. So you can just multiply by 6 minus 2, which gives you another 4, doesn't it? If that's freaking you out, I'll show you what's going on. I don't want anyone having a panic attack right now. Okay, so we've got this 8 pi sitting outside, right? And then 1 to 2, those are my limits for r. So you could just do that separate, r squared dr. And then 2 to 6 are my limits for z, and there isn't a z, so that's just dz like that. And then you can imagine if you took the antiderivative, you would just get z evaluated from 2 to 6, which ends up being 6 minus 2. That's where the 4 comes from. So then this whole thing, whoop, that's just 4. So that's why you can do that shortcut, okay? So we've got a 4 here times this 8 pi. So then I've got 32 pi sitting here. And then integral 1 to 2 r squared dr, that's just going to be 1/3 r cubed from 1 to 2. So that's 32 pi over 3 times 2 cubed is 7, or no, 2 cubed is 8, and then minus 1. I already, look at me, my brain's going. I need breakfast, I'm sorry. Okay, 32 pi over 3 times 7, that's going to give us 224 pi over 3, and that's the end. That is the end. And then you probably saw I gave them some extra credit. I just put actually old like problems from earlier in the semester as extra credit problems. Write parametric equations for the tangent line to the curve of intersection of the surfaces. And I had another Lagrange in there. I'm not going to solve those. That's enough. I don't know if your final exam is cumulative or not. Really, like the last unit involves everything you did all semester. So that's why I really heavily put it on the last chapter. And just that first problem, the first couple, is just like to give them something a little more tame. So they're not doing like all chapter 16 vector calculus problems on the final. But all the final unit involves triple integrals, partial derivatives, dot products, cross products, you know, everything you learned all semester you need for this unit. Maybe that's why it's so traumatizing. I'll make a video later where I put that little chart that I use to summarize and help my students figure out work, flux, divergence theorem, Stokes theorem, Green's theorem, how, they're related to each other. I can do a little summary for you guys coming up soon. But anyways, I hope this helped you just kind of get an idea where you're at. Your final exam might look totally different than mine, but you can hopefully at least pinpoint maybe which topics or sections you're a little weaker on that you might need to go back and review right now. So if you made it to the end, please let me know. What was your favorite question on the exam? I love divergence theorem, but now I do enjoy a good Green's theorem, Stokes theorem. I used to hate them before, but I've gotten over it. And that's pretty much it. So give the video a thumbs up. Subscribe if you haven't already. Math with Professor V. You can also follow me on Instagram, TikTok, Twitter, Math with Professor V again. Yep, I'm everywhere. I love you all. I'll be back sooner than later. Bye.